Number 65 in this section of 4.1 comes from the second batch of problems that I assigned, where they're asking you to approximate a weird value. And so this problem is a little bit tougher than the first set of problems, but I think this better illustrates for us what it is that linearization is actually good for. What we've got right here, guys, is a weird expression right here, the inverse cosine of 0.52. So 0.52 is a valid value for what inverse cosine could be. It could be anywhere between -1 and +1, but it's not one that you guys were supposed to know. It's not one of the nice 16 angles that's out there. So this is something that linearization can help us do. They're not asking us to find this value, they're asking us to approximate it. So what are we going to do? This is really a linearization problem. So what we've got to do is figure out two things right at the get-go. We've got to try to figure out what the function is that we're talking about right here, and then also what the a value is where we're going to center our linearization. Well, coming up with the function hopefully isn't that bad. We're doing the inverse cosine of some ugly number. So the function is just going to be inverse cosine, but I'm not looking for a number here, guys. It's just inverse cosine of x. That's the function. And the a value now needs to be the number that is closest to this number right here that you can actually cleanly evaluate in this function right over here. I don't know the inverse cosine of 0.52 or 0.51 or 0.53, but I do know the inverse cosine of 0.5, otherwise known as 1/2. And we'll get to that in just a second. So what you had to do on this group of problems is come up with the function and the a value, and now, for a little while anyway, this is just like the problems you did earlier. We're going to find the linearization of this function here, f of x, at this a value of 0.5 or 1/2. So here we go. I'm going to take f, and I'm going to evaluate it now at this value right here. So f of 0.5 is going to be the inverse cosine of 0.5. So what angle between 0 and pi over 2 has a cosine or an x value of 1/2. It's awesome if you guys just know this and have it in your head, but for those of us who need a little bit of help, let's take a look. I want to know where cosine, which is x, is positive 1/2. So my x values, 0 right here, 1 right here, and 1/2 is right in the middle. So if I draw that vertical line of x equals 1/2, there's two angles. One here, I didn't draw this very well, guys. That's a pretty terrible circle. Anyway, one here in the first quadrant, one down here in the fourth. Inverse cosine angles only come from the first and second quadrants. So forget about that. I want this angle. And my question then is, again, pardon my bad drawing, that circle should be taller than it is. What can we do right here? I can't change that now, can I? Give me just a second here, guys. I wonder if I can. What if I took this? Okay, there you go. Now that looks a little more like an actual circle. All right, as I was saying, what's the measure of this angle right here? That's going to be 60 degrees, or as we like it in radians then, pi over 3. Okay, so that tells us that our point of tangency is the ordered pair 0.5, maybe 1/2 would be better. I'll write that for now, we'll see. And then pi over 3 is our y value right there, and that is your point of tangency. Good deal. Okay, as pretty as this diagram was, I think I'm done with it now, so I'm going to get rid of it. That was sad. All right, thanks though, buddy. You went down a hero. All right, now we got to work here on coming up with our slope of our tangent. We need our derivative now. So f prime of x is going to equal, and we know this from the end of chapter 3. The derivative of inverse cosine of x is going to be -1 over the square root of 1 minus u squared. Well, our u here is just x squared, and then times the derivative of u, that's just a 1. So that's it for the derivative. And now we're going to do f prime of this a value right here, and I definitely think the fraction is better for us here, 1/2. So what does that do, guys? We've got -1 over the square root of, and that's a 1 minus, and let's cut to the chase right here, 1/2 squared is going to be 1/4. Now, why did I prefer it written that way? Fractions are much easier to deal with here. Let's see if you can figure out what I mean. -1 over, and what's going on here, guys? Now, I'm going to change that 1 into a 4 over 4. And 4/4 minus 1/4 is 3/4. But wait a minute, rather than writing this, the square root of 3/4, let me think before I do that. I'm going to split that up. The square root of a fraction is the square root of its numerator over the square root of its denominator. So I'm going to write this now as a complex fraction, the square root of 3 over, and rather than writing the square root of 4, I'm going to make that a 2 right there. And what I'm trying to get you guys to remember, the denominator of your denominator actually ends up here in the numerator. So this ends up becoming negative 2 divided by the square root of 3. Now that's all we're going to do. You could make that negative 2 root 3 over 3, but you guys don't have to rationalize denominators at this level. That ugly value right there, you guys, is the slope of your tangent. So if you look at the two things we underlined here, we have the point of tangency, we have the slope of the tangent. We're now ready to put all of this together now to come up with the equation of our tangent line. So I'm going to go to purple right here. I'm going to move up a little bit right here. Okay, there we go. And let's get started. We've got y minus pi over 3 is equal to your ugly slope of negative 2 over root 3, and then x minus 1/2. Now that's in point slope form. We want this in slope intercept. Normally what we would do here, guys, is we would distribute the slope in there, but something bad is about to happen. This times this is going to be pretty ugly. We're going to end up with what? A positive, okay, the 2's will cancel, 1 over root 3. Our next move then is going to be to add this pi over 3 at the end. Well, 1 over root 3 and pi over 3 are not like terms that we can combine right there. So what I'm going to do instead, I'm going to try to force myself to do this a little bit more, is do something that the book does a lot, which is called point slope equation. In fact, I'm going to write that here, PSE. It sounds obviously like point slope form, but it's got one little difference right there. It's still solved for y, but all you're doing now is adding this k value, pi over 3, on both sides, but you don't distribute the slope right here, guys. You leave it factored out. So it's negative 2 over root 3 times the binomial of x minus 1/2, and then you just stick on this plus pi over 3 at the end, and that is where you stop. So it's kind of cheating. It is solved for y, so it's like slope-intercept form in that regard, but it's not quite slope-intercept form because the slope hasn't been distributed. It's still factored out, but there's no point in doing it because you wouldn't be able to combine your two constants. All right, guys, that is our linearization. Whoop! The only change being I'm going to get rid of that y, and I'm going to make that here an L of x. So in the previous batch of problems, this is where you would have quit. But now what they want us to do, everybody, remember, look at our directions, is to approximate the value of inverse cosine of 0.52. So I'm going to write something that seems insignificant here at the end, but here goes. We're trying to figure out, let's get this down right here, the inverse cosine of 0.52. That is the same thing as saying, what is f of 0.52? And now here's the significant thing. F of 0.52 is approximately equal to L of 0.52. That doesn't look significant right there, guys. It's really easy to overlook, but that's the significance of what we're doing here. We came up with a linear function that can be used to approximate an ugly value in a real function. And the thing about linear functions, guys, even when they're pretty nasty like this, they're not that hard to evaluate. So I'm going to keep going with this. Here's my approximately equal to. Let's get working on evaluating this. So I'm looking right here. We've got a negative 2 over a root 3. And then in parentheses, all right, I've got a 0.52 for x minus, all right, now I better change that 1/2 back to a 0.5. And then a plus pi over 3 at the end. Ugh. Now, the hope of this would have been that we could come up with a relatively nice value without needing our calculator. I'm not really sure that's going to happen. This right here, guys, is going to be a 0.02. Okay, and then we multiply that by this fraction here. So I guess that's a negative, multiplying that by 2, 0.04 over the square root of 3. That's not very pretty. And then plus a pi over 3. Now, at that point, if you guys were to quit right here, I'd be fine with that answer. However, I want to know, I don't know about you guys at the end of this, if I was actually right and if I was actually close. So I'm going to grab my calculator. I just have a scientific in front of me right here. And I'm going to type in what I have written there at the bottom. Negative 0.04 over the square root of 3. Gotcha. And then at the end of all that, I'm going to add a pi divided by 3. And that gets me this rather ugly value here of 1 point. I've got 0.24. Okay, so I'm good with either that answer right there or that answer right there. But just for fun here, guys, I'm going to take advantage of the calculator I have right here, and I'm going to actually ask my calculator what is the inverse cosine of 0.52, all right, which of course with modern technology is pretty simple for us to get, but even 50 years ago this would have been pretty hard. So I type that in. Okay, wait a minute, you're going to want to make sure your calculator's in radians and not in degrees, kids, because that's going to give you an answer that's nowhere close. All right, let's try this again now. Inverse cosine of 0.52, I type that in and I got a 1.024. Actually, it's 0.239. I'm going to keep going here so you can see how close we were. 945,376. The answer I came up with a moment ago, I didn't write that down in great detail, 1.024. So the thing is, if you round to 3 decimal places as we normally do, you would have gotten the exact right answer of 1.024. Now, as you go further, you can tell that these two numbers are not quite identical. And I'm certain that however my calculator was programmed, this answer is more accurate than this answer, but they're pretty darn close, everybody. And if we were building a bridge or trying to send a rocket into space, hopefully, that would be close enough that the results wouldn't be disastrous. So that's how you handle those problems, guys, at the end of section 4.1. You're finding the equation of a tangent line, and you're sticking in this ugly value, in this case 0.52, and coming up with our approximation using linearization.